So one of the most basic types of differential equations we have solved a lot of times. So that would be dy dx equals g of x. So in order to solve this, we say y is the integral of g of x dx. So we get capital G of x plus a constant where g prime, big G prime is little g. So that's our most basic kind of differential equation, I think. I would say it's the most basic kind. This is a special case of a separable differential equation. Separable differential equation is one that we can write dy dx is g of x times h of y. We have a product where the components of the product are a function of x and a function of y. We call this a separable equation. Or we say that it has separated variables or separable variables. So any equation that we can write like this, where a product of a function of x times a function of y, is a separable equation. And now, just to kind of extend this a little bit, if you go on and you study partial differential equations, you kind of do a similar thing with partial differential equations, where you assume that the solutions have separated variables, and that gives you a way to go about solving those. And then if you have uniqueness, once you find a solution, it is the solution. So an example, we might get something that looks like this: e to the xy dy dx equals e to the minus y plus e to the minus 2x minus y. And we want to solve this. Well, the way it looks now, it looks kind of messy. But we can rewrite this as e to the xy dy dx. We remember our properties of exponents. The computer has been having some issues lately. Plus e to the minus 2x times e to the minus y. And then we can factor. So that's e to the minus y times 1 plus e to the minus 2x. And then we can divide by e to the xy, and we get dy dx is e to the minus y over y times 1 plus e to the minus 2x over e to the x. And there is our equation with the variables separated. And then we can go about solving this. But something like this, dy dx is y plus e to the x. Much simpler equation with a function of x and a function of y, but this is not separable. So as it's kind of arguable, as long as we're as long as we're good at integration, this equation is easier to solve than this one. And do we remember how we go about, or in the past when you've seen these, how you go about solving them? Yeah?
Maybe just integrate both sides.
So, yeah, so the way we thought about it is we get x's together. So get x's on one side, y's on the other, and integrate. So that what we're saying is if dy dx is g of x h of y, what we would do is, the way we think about it is, we divide by y and multiply by dx, and we say that the integral of dy over h of y is the integral of g of x dx. Now technically, we're not, we can't really treat dy dx as a fraction. We're not really multiplying both sides by dx, but we can think about it that way. So what we are doing, this is, we're being very loose with the terminology here. So I'm going to say what is actually happening. This is not this class is not heavy on the y's, other than it works. But this is one place where I want to be clear about the y. So we're given dy dx is g of x h of y. And I'm going to write that 1 over h of y dy dx equals g of x. I can divide both sides by h of y. H of y is just a function of y. If y equals phi of x is a solution, then we have to have 1 over h of phi of x dy dx is going to be phi prime of x. That has to equal g of x. So I'm just substituting phi of x for y. And we can integrate both sides with respect to x. The integral of 1 over h of phi of x, phi prime of x dx equals the integral of g of x dx. We can take the integral of both sides with respect to the same variable. But phi prime of x dx equals dy. If we're thinking of our little increments on the x-axis, if dx is a little increment on the x-axis, the amount that we change in the y direction is the slope times the distance we travel along the x-axis. That's going to give us the change in y. And we can prove this rigorously using limits, letting the dx approach 0. This is okay to make this substitution. So we can write finally, that transforms into 1 over h of y dy equals the integral of g of x dx. Phi of x is y. So this is what's actually happening there. We can think about it as multiplying both sides by dx. We can, in this case, we can manipulate those as if they are fractions, but that's not actually what's happening. Yes?
So it only works if y is a function of x, right?
Yes.
Okay.
And for what we're doing, we're assuming that y is a function of x. All right, so I just want to go through a couple of examples to show the procedure, to point out some interesting things that happen here, and also talk about how we can look at graphs of the solution curve if we can't get an explicit solution. X square root 1 plus y squared dx. And there's also some interesting, some nice math that goes on here as well. Y square root 1 plus x squared dy. And we want to solve this. And I think with this one, it's pretty easy to see that we can gather the x's together and gather the y's together. If we wanted to, we could check, and we could rewrite this as dy dx equals x over the square root of 1 plus x squared times the square root of 1 plus y squared over y. We could rewrite it like that. So I can write y over the square root of 1 plus y squared dy equals x over the square root of 1 plus x squared dx. So that's pretty nice. We integrate both sides. A lot of times with these equations, we don't really write unless there's some extra work in evaluating the integral. We can evaluate the integral directly. So we're integrating both sides. The integral of y over 1 plus, oops, my thing died. Let me get some power here. Y over 1 plus y squared and x over 1 plus x squared are just nice, nice u subs. So I'll write out that we integrate. So integrate to get square root 1 plus y squared equals the square root 1 plus x squared plus c. We just gather all the constants on one side of the equation. And we can say y equals the square root of 1 plus x squared plus c squared plus 1. That would be our explicit solution. Oh, minus 1. So there's our explicit solution to that differential equation. And if we had an initial value problem, we could substitute. I'd probably solve for the c here, just because it's outside of any other functions. If we had an initial value problem, we'll see an initial value problem in the next one. All right, questions there? So separable differential equations, when you solve them, you're going to have at least 2 integrations for every problem. Questions? Okay, let's look at another one. This one has a nice thing that comes up here. 1 plus x to the 4th dy plus x times 1 plus 4y squared dx equals 0. And we have y of 1 equals 0. And we want to solve this. I'm going to do an intermediate step here. I'm going to subtract 1 plus x to the 4th dy equals negative x times 1 plus 4y squared dx. So dy over 1 plus 4y squared equals negative x over 1 plus x to the 4th dx. We have a interesting, I'm going to write out the integrals this time. The integral of dy over 1 plus, and I'm going to write this a little different way, 2y squared equals the integral of negative x over 1 plus x squared dx. These look a little more familiar. These are both inverse tangents. So here, if u is 2y, du would be 2y dy. So we have 1/2 inverse tangent of 2y equals, and here, if u is x squared, du is 2x dx. So we have minus 1/2 inverse tangent of x squared plus c. So inverse tangent of 2y equals negative inverse tangent of x squared plus some c1 if I multiply by 2. A lot of times when we're multiplying by a constant, often you'll see the c just stay as c. For me, I need just to keep, not to get myself confused, I write c1 just to tell myself I multiplied this by 2. It's not really necessary, it's just a constant. For me, it helps me to keep it lets me be okay in my head. Mostly okay in my head. Now I'm going to find my constant when x equals 1, y equals 0. So we have the inverse tangent of 0 equals negative inverse tangent of 1 plus that constant. Well, the inverse tangent of 0 is 0. Inverse tangent of 1 is pi over 4. So c1 equals pi over 4. So let's substitute that in, and we'll have a little more work to do. An implicit solution is inverse tangent of 2y equals negative inverse tangent of x squared plus pi over 4. That would be a specific solution to our initial value problem. But what if we want an explicit solution? Going to take the tangent of both sides. So 2y equals the tangent of negative, I'm going to change the order here. I'm going to say pi over 4 minus the inverse tangent of x squared. Well, that's okay-ish. Somewhere in the back of our memory, we should remember that there is a formula for the tangent of the sum of two angles. There is tangent of a plus b, or sorry, a minus b, because we have a minus there. Tangent a minus tangent b over 1 minus tangent a, or is it 1 minus? 1 plus. 1 plus tangent a, tangent b. Would I necessarily expect you to remember this formula? No. Would I expect you to remember that there is a formula? Yes. Would I expect you to be able to use it if you're given that formula? Yes. So we get 2y equals tangent pi over 4 minus the tangent of the inverse tangent of x squared over 1 plus tangent pi over 4 times the tangent of the inverse tangent of x squared. I have enough parentheses there? Yes. Okay. So 2y equals tangent of pi over 4? 1. What's the tangent of the inverse tangent of x squared? X squared. 1 plus x squared. Or sorry, this is a minus, isn't it? Minus, yes. Over 1 plus the inverse tangent, or the tangent of pi over 4 is 1, and the inverse tangent of the inverse tangent of x squared is x squared. So we get, finally, a nice function. Y equals 1/2 1 minus x squared over 1 plus x squared. That's not a terrible function. Yes? So we're assuming that here we're assuming that we're going to get our result is going to be between negative pi over 2 and pi over 2 to allow us to do that. Isn't that fun? That these things come back in unexpected, mysterious places, and then when we use them, they're really nice. There are formulas, just be aware, for future reference for the sums and differences of all of the trig functions. Sine of a plus b, cosine of a plus b, sine of a minus b, cosine of a minus b, etc. So if you integrate and you get a cosine of y squared equals the cosine of 3x plus c, you can get an explicit solution there. Yes?
So like, you said like on tests, if we like are expected to explicitly like go to the staff formula, or is that one which I don't know?
I would give you that formula.
Okay.
I would just expect, in the homework, I would expect that you would know that there is a formula and then be able to use it once you looked it up or asked what the formula is. All right, let's look at another one. This time we're going to find our solution and the interval of definition, because that is important sometimes. Sine of x dx plus y dy equals 0, and y of 0 equals 1. So I have sine of x dx equals negative y dy. So we integrate both sides. And we get that negative cosine x equals negative y squared over 2 plus c. And when x equals 0, y equals 1. So we're using our initial condition there. We get negative cosine of 0 equals negative 1/2 plus c. So negative 1 equals negative 1/2 plus c. And that tells us c is negative 1/2. So our implicit solution is negative cosine x equals minus y squared over 2 minus 1/2. And I could rewrite this as y squared equals 2 cosine x minus 1. For an explicit solution, I'm going to say y equals the square root of 2 cosine x minus 1. Why not plus and minus? Y positive since y of 0 is greater than 0. Y of 0 is 1, so we have to have the positive solution for our interval of definition. But we have this radical here, and we need 2 cosine x minus 1 to be greater than 0. So that means cosine x is greater than 1/2. So we have negative pi over 3 less than x less than pi over 3 for cosine x to be greater than 1/2. And this interval must contain x equals 0. Because there are other intervals between which cosine is greater than 1/2, but that interval has to contain x equals 0 for it to contain our solution. And what other condition do we have? Looking at our equation. If we solve for dy dx, what would dy dx be? Dy dx would be sine x, negative sine x over y. So y can't be 0. So this is our solution. Y equals positive square root of 2 cosine x minus 1. For this particular equation, this particular initial value problem, we need x between negative pi over 3 and pi over 3, and y can't be 0. So because of that initial condition, we have to be careful with our solution, distinguishing between our solution as a function and our solution as a solution to the initial value problem. This is kind of why I say that when we have this, we have to do all this. That's why numbers mess things up. If we didn't have those numbers, then we just have nice functions. All right, the last thing I want to say today about separable equations before we have time to practice. Often, well, sometimes, maybe not often, well, no, I'm going to say often, it's difficult or impossible to get an explicit solution like this. And so then maybe we want to look at the solution curves. We want to get a sense of what our solution looks like in the plane. So if it is difficult or impossible, you can plot contour lines, contour plots. To see our solution curves. So, for example, if we had, say we solved a separable differential equation, and we get natural log of y plus y natural log y equals 3 sine x. Sorry, 3 plus sine x is what I wanted. I'll do sine x plus 3. That would be, I would say, impossible to solve for y explicitly in terms of x. So we can say f of xy equals natural log y plus y natural log y minus sine x equals 3 sine x. So this is f of xy equals a constant. We can think of this as a level curve of f of xy. And the constant is 3. So I'm going to go to, I have a contour plotter bookmarked in our Schoology class. So that's a Desmos. Contour plotter. So let me go there. Well, let me do this before, see if I've timed out here. Oh, and I put another thing in that folder yesterday as well that we'll need for this chapter. So there is the contour map grapher. It's pretty easy to use. So these I don't change. This is our function, f of xy, and I'm going to put our function in there. What did we have? Natural log y plus y natural log y minus sine x, and our constant, I'm going to change it down here, equals 3. And there's a contour plot of our solution. And you can change your constants down here on this last. So if we had 5, that would be, we had 1, and this is just for various values of c. So those are what our solution curves would look like. It's kind of interesting that the sine x kind of dominates. All right, questions? I'm just going to grab a picture of this to put in the notes. Oops. There we go. and then I'm going to go back here. This was when C was 3. Is that one? It was here-ish, but I think it's a little different. Not exactly our solution curve, but it's close. All right, so there are some questions, some of your homework problems where you can't solve for an explicit solution, and it asks you to use a plot a contour map to see to get it to sketch the solution curve. So you have that Desmos plotter that will do that for you. So you don't have to do it by hand.
Mr. Damon,
Yeah.
I have a math joke for the video.
Okay.
Why was the equal sign so humble?
Okay. Why was the equal sign so humble? I don't know why.
Because it knew it wasn't less than or greater than anyone else.
Wasn't less than or greater than this.
Shut up.
Very
Shut
nice.
up.
EOO is every other odd.